So, yeah, this week we got 2.03, 2.04, 2.05, we got 3, and then we have another test next week. This is a short unit, 5 lessons, and then we jump into a test over this. This is about functions, building functions from functions lessons. So we're taking 2 functions and manipulating them together in different ways in this lesson. So let's pull that up on the screen and take a look at what that means. All right, so we're talking about combinations of functions. So if we have f of x, let's just put some examples out here with an f of x and a g of x. And let's see, well, let's see if I can use one from their examples just to give you something. Okay, so if we have x squared is what f of x is, and g of x, let's say, is just x plus 1. Let's just make it simple. We have our f of x and we have our g of x, x squared and x plus 1. Get a little brighter. See if that helps any. And we're doing the following things with functions in lesson 2.03. We are going to look at adding them, subtracting them, multiplying them, dividing them. We can do the same thing with functions that we do just with any numbers. So if we have f plus g of x, okay, f plus g of x, that means we're literally taking these 2 functions and combining them, adding them together. That would be the same thing as taking f of g and adding, not f of g, f of x. We're going to talk about f of g, f of x, and adding g of x to it. So in this case, we would have x squared plus x plus 1. So f plus g of x is x squared plus x plus 1, because we took this and we added this to it. If we have f minus g of x, we have same thing as taking f of x and subtracting g of x, which is x squared, and we're subtracting all of it, x plus 1, which means we would have to distribute that since this is a minus. So this would be x squared minus x minus 1, because we're subtracting the entire function. So you'd want to use parentheses to start out with to make sure you don't forget that we're subtracting both terms, and we would end up with a minus x minus 1. We can do fg of x, which is multiplying. When we have 2 variables right next to each other, that's multiplying. That's the same thing as taking f of x and multiplying it times g of x, which in this case would mean taking x squared and multiplying it times x plus 1, which would be x squared times x is x to the 3rd, x squared times 1. So that equals x to the 3rd plus x squared. That's right, Antonia. Welcome to class. So you can always look at the video to see what you missed. I just started those, so it's all right here on this page. So this is multiplying. So we end up with this when we multiply. We end up with this when we subtract it. We end up with this when we add. There's 1 left, and that is f divided by g of x. F divided by g of x. That's the same thing as taking f of x and dividing it by g of x, which is just quite literally x squared over x plus 1. And we can leave the answer in that form right there. X squared divided by x plus 1. So that is what 2.03 is like starting out with. Taking functions and being able to manipulate them mathematically. The other thing we look at is compositions of functions in this lesson. And this is where I talk about f of g of x. We're like, oh my goodness, what is that? Well, that's a little different than any of these four. It's not the same as f times g. Because anything's like f of x, we're solving this for whatever x is, right? G of x, we're solving this for whatever x is. And this, we're solving f for whatever g is when x is this. So one thing it could do, it could say evaluate, and we'll use these same two functions up here. It'll say evaluate f of g of x when x equals -2. So to do that, first we've got to take the inside of this, g of x. What is g when x equals -2? So g of -2 would be substitute -2 in for the x, -2 plus 1, which is -1. So g of -2 equals -1. So now we go back and we find what is f of -1, because that's what g of x is. When x is -2, g of x is -1. So what is f of -1? Well, we put -1 in there for x. It would square it because that's what the function f of x is. And -1 times -1 is a +1. So that is what this equals. It equals 1. So when it has you do f of g of x, you're taking g of x and you could also do just as easily g of f of x. Let's do g of f of x when x equals -2. And most of the time, it's going to be different. And I want to divide these out where we can kind of see it. So when x is -2, now we've got to do f of x first, because that's what's on the inside. We've got to start inside out. What is f of -2? Well, it's x squared, so it's -2 squared. -2 times -2 is a 4. So then what is g of 4? 4 plus 1. This equals 5. So f of g of x equals 1, but g of f of x equals 5. Does not end up the same a lot of times. It can end up the exact same, but a lot of times it's not. And we'll talk about cases where it's going to end up the same here just briefly too. So this is a summary of what we're looking at in this lesson. We're looking at adding functions together, f plus g. We're looking at f minus g. We're looking at f times g and f divided by g. Add, subtract, multiply, divide. And then we look at putting them together in a composition, f of g of x. So when you read through our lesson, it does give this summary at the top and talks about it in very mathematical terms a lot of times. But then you get into the lesson, which is real early. It's only on page 2. You'll start the lesson. It will give examples. When you're reading through this is a very college level textbook that we're using in this unit. A lot of the math terminology has at a very high level. If you don't understand some of it, bring questions to class or email me, get with me, and I'll be happy to explain that. But read through it, understand what these examples are showing us, and sometimes they help us understand, like the composition of functions, f of g of x. The definition it gives is let f and g be two functions such that the domain of f intersects the range of g. So that means the domains has something in common with the range of this one. The composition of f of g denoted f, and they also denote it this way, f with a little circle g, f of g is defined by f of g equals f g of x. So they define f of g to be f of g of x. That's the same thing. And the domain of this consists of all the x values in the domain of g that map to the g of x values in the domain of f. So it's very wordy, but it's saying that all of the y's from the f are going to be the x's and g as far as the domain and range is concerned, because they have to have some commonalities. And then they give you some some diagrams that have some circles and arrows and all this, and it can get a little bit confusing. But pay attention to the examples because that's the main thing. Do you understand the examples? Do you see what it's doing in there? They do some graphs, they do some extra things like that. But go through the examples, read those, make sure you understand what you do. If you need to write those down and go through the steps yourself to help, you can do that as well. But I'm trying to give you some good examples right here that just take two functions. This one's quadratic, this one's just linear, and being able to do this. We could do this with two linear, we could do quadratic. It doesn't matter what kind of functions, as long as they're a function, right? As long as it's a function, and we can manipulate those. So they have some more examples using some others with square root functions and quadratics. Square roots and quadratics go real well together because the square root is the inverse function of squared, right? So if we have a square root of 2 squared, it's just 2 because they cancel each other out. But that is just a quick overview. This is an overview of everything that is in lesson 3. So let's look at lesson 4 now. Lesson 4 talks about inverse functions. Okay, inverse functions. So let me turn this over and let's talk about inverses. So let's start with their mathematical definition about talking about the inverse of a function. If the set of real numbers, and they give us a set, right? A set is of these numbers. So this is the only numbers that you can use for the domain. So they say this is the domain of this function. 1, 2, 3, and 4. That means it does not include 1.5 or 2 3/4. None of those numbers exist, just these 4 numbers. And then it says, then the range 2, 4, 6, 8. If they gave this as the range, all right, this can be noted as f of x equals 2x, because you see when the domain is 1, the range is 2. That's 2 times. Each of them is 2 times. And then it gives all the points. 0.1, 1, 2 to 0.2, 4, 3, 6, and 4, 8. So they're defining this first off. So if we talk about the inverse of this function, the inverse would be the set. This is the inverse. 2, 1, 4, 2, 6, 3, and 8, 4. The inverse will reverse. Oh, I need to close my bracket. Reverse the points. And this is how an inverse function is noted. We put this little -1 up here. This does not mean f to the -1 power. This is not an exponent. This is how we denote inverse functions. All right, that's the way we label an inverse function. We use this little f1 above the function. So this is function, this is inverse function. Function, inverse function. So basically these are opposites. They kind of undo each other. The function, inverse function. So this would be 1/2 x. Right? This one's 1/2 x. Because on this one we multiply 2, this will multiply by 1/2, and we get backwards. And they're opposite of each other. So what we find out is if we have f of the inverse, we just talked about in the last lesson, that we could do a composition. If we take a function and its inverse, all right, so if the function is 2 of x, but instead of x, we're going to substitute in the inverse 1/2 x. 2 times 1/2 x. 2 times 1/2 is just 1, so it just equals x. Let's do it the other way around. If we take the inverse of the function, which means we have 1/2, and then instead of x, we're going to put in f of x, 2x. 1/2 times 2 is 1. Again, we're just x. If you have a function and its inverse, and we do the composition of them, we will always end up with just x. That means they are truly inverses. We'll always see that. This is the identity function x. So when we take an inverse and we do the composition with this function, It'll end up, it's one of those times where they end up the same because they're inverses. So it will always do that. And so it has a definition of an inverse function. Two functions are inverse functions if, for the functions f and g, f of g of x equals x for every value in the domain of g, and g of f of x equals x for every x in the domain. So this is, if we called this g of x, which is the inverse function, we said the inverse, if we named it g of x, then f of g of x would be x and g of f of x would be x. And that's how we know they're inverses. That's a definition of inverses, that they end up that way. So it gives you a function to test your skills. Determine the inverse function. Now, let me tell you how to find the inverse function. Let's make it a little more complicated. Not much, but let's just say it is 2x plus 3. And we want to know, what is the inverse function of 2x plus 3? This is how you find the inverse function. First, let's put it back in the y notation instead of function notation. Let's use the y. So we substitute it back to the y. Right? So this is the same thing. This is just using function notation. After we do that, let's swap the x and the y. I'm going to put the x over here and put the y. I just traded places. The y and the x traded places. Now I want to get this back to a y equals. I'm going to solve this for y. So I'm going to subtract 3. So we've got x minus 3 equals 2y. Divide by 2. So x minus 3 divided by 2 equals y. This is the inverse function. Equals x minus 3 divided by 2. This is the inverse of this. So when we find the inverse, we do that by writing it as a y equals, trading places with the x and the y, and then solving this for y equals. When we get this back to a y equals, this is the inverse function. And we can do that with any function. We can make it a little more complicated. Let's say it is x squared minus 2. That's our function. Now, what's the inverse of that? Okay, so y equals x squared minus 2. X equals y squared minus 2. We trade places. Solve this for y. We've got to add 2. X plus 2 equals y squared. We're trying to solve this for y. That means we have to take the square root. So y equals the square root of x plus 2. So the inverse is the square root of x plus 2. We're going to deal a lot with radicals. Square roots, anytime we're doing inverses, if we have a squared, the inverse is going to have a square root. Square root of x plus 2. These are inverses. And if we did this, where we substitute one to the other, we'll end up with x. Let's put this in here. Let's do f of f inverse. And this should end up with just x, right? If they're inverses truly, we should end up with just x. So instead of x, we're going to put this in there. Square root of x plus 2 squared, because we substituted into x, minus 2. All right, so we took this and we're substituting in for this x. So the square root of something squared cancel each other out. So this is just x plus 2, because we squared a square root. Minus 2. X plus 2 minus 2 equals just x. So it should just equal x if it's an inverse of each other, which it did. Okay, now let me show you a graph of what it looks like when we take the inverse and we graph that. The first one we had was 2x. And the second one we had was 1/2 x. That is the two graphs. Now, there's something to be true about a function and its inverse, is that there's a line, y equals x, that diagonal green line you see. The graph of a function and its inverse will be reflection over that diagonal line. So it's a reflection over that y equals x line. Let me turn off the second one. See, there's the first one, that red line, and the reflection is the blue line. All right, let's look at this other one we did with the x squared. So if we have x squared minus 2, there is the graph of that. And we said that the inverse is the square root. So use the square root, and I'm going to put this in parentheses, so it's all under the square root. We said the inverse was x plus 2. And notice it's domain limited here because it doesn't have negative values for that. But we see it meets right there. That is a reflection over the line. Let me close this down. That is a reflection of the y equals x. Being a square root, it's not graphing any negative values. Because in the real world, it doesn't have a negative value for that. Because it won't have a negative result. It's only doing the positive. Although really, in the square root of something, we can have a positive or negative square root. We just got to have a negative underneath the square root. But that is also a reflection. If we limit the domain on the first one to say x is greater than 0, we see the true reflection there. That's where the domain and the range. The domain of this one is the range of that one. But it's a reflection over that y equals x. So that is something that is true of a graph of a function compared to the graph of its inverse, is the reflection over that diagonal y equals x line. It has the points 2, 2, and 1, 1, and 3, 3, and 4, 4. All of those points are on that. All those points are the x equals the y. It's important to note that not all functions have inverse functions. Not all of them have inverse functions. They have to be what we call a one-to-one. One-to-one. So let me show you how we can tell that. Basically, no two elements in the domain would have to have the same range, which means this is one of those to where if we had a table and we were looking at the values, and when we have -2, -1, 0, 1, and 2, before we talked about a function, we said this could be 0, 1, 2, 3, 4, and that's fine. And we also said that it could be a function if all of these are 2's. Each x only has one y. They happen to be the same y, but each of them only has one y. This is a function, but this function does not have an inverse because the same y is used more than once. There has to be unique values in both columns. There can only be one element in the x. It can only show the domain one time. We can only see -1 one time in the domain. We can only see 2 one time. And we can only see the same number in the range one time. When the range repeats, it does not have an inverse. We can also see that when graphing, we talked about when we look at the test to see if something's a function, we use the vertical line test, right? Draw a straight up and down line anywhere. If it crosses the graph twice, it is not a function. To find out if it's one-to-one, we can do the same thing with a horizontal line. We draw a horizontal line, and it only crosses the graph once. This one is one-to-one. If we look at the graph of x squared, just the graph x squared, this is not a one-to-one. Not one-to-one because it crosses twice when we do a horizontal line. So the existence of the inverse function, if no two elements in the domain point to the same in the range, so we run into some problems if it's one-to-one. That one's not one-to-one. All right. So just know on the graph how to tell if it's one-to-one using the horizontal line test. Right. Let's look at our last lesson this week, and it is talking about graphing transformations. All right, so transformations. What happens when we transform a graph? How do we do that? So in our lesson, there's going to be a link right off the bat, the graph of the most common functions. But we have the constant function, which is just a horizontal line where it just equals a number, that's c. We have the identity function, that's that diagonal y equals x. We have a squaring function where we have an x squared, we have a cube, x to the cube. So this is linear, this is quadratic, and this is to the third power. The square root function, and then the absolute value, where it's like a mirror reflection of the y, and it's a straight line, but it does not have any negative y values. But we can transform any of these. And when we transform these, we will be able to move them in all kinds of ways. So let's look at that. All right, let's talk about horizontal and vertical shifts. So if we have a graph, and let's just choose one. Let's just choose quadratic, right? We know what a quadratic looks like. It looks like this right here. We can shift it vertically, which is up and down, by simply adding a constant after it. We just add a constant, whatever number. If we add x squared plus 5, what that does is it moves this from the origin up to 5. It'll be up here. It'll be up at where y equals 5. That will be the vertex. That'll be the lowest point when we add this. If c is a negative number, x squared minus 2, now it's going to move it down here to negative 2. And the graph is going to be not touching there, touching the negative 2. That's how we move it up and down, is by adding a constant after the x squared. Actually, that's how we move anything up and down, even if it's just an x, right? Y equals x. If we add a plus 2, it just raises the y-intercept up to 2. Anytime we just add a constant on the end, that's going to make a vertical change up and down. There are also ways to make this shift left and right. So for the x squared, if we take this and we say f of x equals x plus 1 squared, what that's going to do, instead of coming right here to 0, that's going to move it left over here to 1. It's actually going to come right here to negative 1. It's the opposite of what you would think. You put it in the parentheses, so it's with the x. Otherwise, if it's after it, if it's minus 1, it just moves it down. But when you put it with the x, which means we put it in the parentheses with the x in this quadratic function, it's going to move it left. It moves it to the negative 1. That's because if we want to go back where we started, we got to add 1. So if we take this and we add 1, that takes us back to where we started. We're back to the usual x squared function. So this tells us what we have to do to get back to where we started from. So this moves left. This moves right. If we do x minus 2 squared, then it's going to be over here at 2. And we'll have the same function over here at 2. So the negative moves it right. The positive moves it left. So that's a little different than what we normally think. X plus 1 squared left, x minus 2 squared moves it right. So plus and minus is going to move it the opposite direction on the x-axis. So they do give you some examples there. It says review the examples. It's got x squared minus 6, x plus 3, x minus 6 in parentheses squared, x plus 3 squared. They do different things. The other thing we can do is a reflection shift. If we took f of x equals x squared, which means it's just the normal graph, right? X squared is just through the origin. And here's what we're going to do. We're going to put a negative 1 in front of it. A negative 1. This coefficient is going to have a negative. That is going to reflect it over the x-axis, because whatever the x was is now going to be a negative x. Whatever the value was. I mean, what a value. If we put in 2 for x instead of being 4, and that's going to be negative 4. So the range is changing and being reflecting over the x-axis. So that is a reflection shift. So this reflects over x. Reflect over x. See, the other things we can do is a non-rigid transformation. These will all look exactly the same. Let's do one more thing to it. If we have f of x equals x squared, all right, so again, we got just the regular quadratic graph, and we change it to be 2x squared. 2x squared. Well, what's that do? It's not going to move it left or right because that's when we add or subtract something to the x. It's not going to move it up or down because that's when we add it at the end. This is going to multiply all the values times 2. So instead of this being down here, it's going to be twice as high. Instead of this being right here, it's going to be twice as high. This is going to be twice. It's going to double the value of all the y's. So this is going to make it taller, faster. I guess is a way of saying that. It's going to be, it's what we call a vertical shift. Because vertically, it's shifting everything up. Instead of being in here, it's shifting it up. It's going up faster. If this number right here is less than 1, then it is a horizontal shift. So let me look at that with you on Desmos, because that'd be much clearer than what I can draw. So there's our common y equals x squared, right? And so when we do a vertical shift, and I'll make it more extreme, let's do 4x squared. 4x squared. So instead of this being 1, now when x is 1, it's 4. See, the y is 4 times as large as what it would have been with just the x squared. 4 times as large. Let me change this to where it just shows the ones in there. 1. Instead of 1, 1, it's at 1, 4. Now let's look at a horizontal shift. I said if that coefficient is less than 1, so let's make it 1/4. Let's make it 1/4 x squared. See, that's the green one now. I'm going to turn off the blue one. The red one is just x squared. 1/4 means it's a lot smaller. So up here, when we're at 2, 4, this is only at 2, 1 because it's only 1/4 the size. 2, 1. Okay, not gonna get it. There it is. 2, 1. This is a horizontal shift because we're stretching it out horizontally. We're making it horizontally wider than it should have been. We're stretching it out. Whereas this one is stretching it up vertically. So if this coefficient is larger than 1, it's a vertical shift. If it is less than 1, it is a horizontal shift. So that's what you want to remember on this. If it's greater than 1, it's a vertical shift. If it's less than 1, it's a horizontal shift. When we're talking about the coefficient. And that can be true if it's x squared, if it's just like a absolute value function, it would do the same thing. It would do the same thing with just a linear function. Anything that coefficient on that first term is going to cause either a vertical or horizontal shift. So that's the things we're looking at in graphing, transforming the graphs by vertical, horizontal shifts. We're looking at moving it left and right by putting it inside with the x parentheses. Look at moving it up and down by adding a constant at the end of the function, or reflecting it by putting a negative in front of it. We're going to reflect it over that x like we did right there. Sure. That is the big picture for this week. Lessons 203, 204, 205. Go through those. Look at the examples. It has some of those that are check your answers, which means it gives you a couple of problems. You figure out your answer and then click on that check your answers. And you probably ought to do all the problems in the box because otherwise you'll see the answers to the ones you haven't done yet. If you just do the first one and click on that, it'll show you all the answers that are in that box that it's giving you sample problems on. So do that, just the problems in there, and then check your answers. And then you can make sure you're getting the same answers, right? So you're getting it right. And then, of course, you'll have some assignments with each of these that you can also use as practice to make sure you're understanding it. Because next week we'll have the practice test and the test for this module before we move into module 3. So if you have questions on this, bring them to class on Wednesday. Let me look and see how we're standing on. I think just about everybody is caught up on the test. Last I looked, there were still a few people that have not necessarily got everything in yet and may still be behind. But if you have not finished the module 1 test, then you are certainly behind. And I only see maybe 1 or 2 people like just a couple of people that have not yet finished the test from last time. We're already in the second week of module 2, so you are getting behind if you've not finished that test. And I've had a few people retake the test from the first module that didn't do well, and you can email me. We can talk about that if that is a case that you need. Otherwise, stay caught up. There's still a few of you that did not finish what was due yesterday. So you want to get caught up with module 2, because we're going to get to module 2 pretty quickly here. We're not going to spend a lot of time on module 2 this week, and testing next week. And then we'll be on module 3. So if you have questions, bring them Wednesday. If your grade's below 70%, you need to be here Wednesday. Otherwise, have a great week. I'll let you guys go. So
let's get out of here. Word to your multiples. Math, baby. We're learning math, baby.